Okay, so the main concepts that we found in Lab 6.1, 6.2 was they all kind of circled around the same equation that we saw, and it's this chemical reaction that we saw, I guess you could say. So if I was to write it down, it all starts with examining an enzyme, and this is what catalyzes this reaction, and that was malate dehydrogenase for short. So essentially, malate dehydrogenase is a string, remember, of amino acids like any protein. And it's this big enzyme, and I don't know if that's how it looks, but what it has is this active site. And it allows a chemical reaction to occur when it otherwise wouldn't. So for our purposes, we have what we had, oxaloacetate in the presence of the electron donor, NADH. And we'll label it here. So we know that this reaction goes forward and it goes back, but we'll get to that. So essentially what this does, this reaction right here, is that it brings these two molecules together because the amino acids in this active site, they match and they bind right here, and they bind right here to NADH and oxaloacetate, and they make that fit happen. Otherwise, these molecules are just randomly kind of floating around. To come together randomly would take a lot of chance and usually just never happens, but our bodies need this reaction to happen. So what we first did was measure, we needed a system to measure this reaction. We saw that there was no excitement by adding oxaloacetate. There wasn't any excitement by, I think, adding malate, which is the product over here. So these are like the spent products. And we found that NADH is actually excited by the spectrophotometer at nanometer. I think it was like 314 or something. I can check. You don't have to know that, but I'm curious. Yeah, 340. Okay, so 340. So we found that we could measure this system by measuring NADH. So we saw that NADH was reduced when we added all the components together. When we added oxaloacetate, NADH, and malate dehydrogenase, this reaction collectively moved this way towards the products malate and NAD+. In the absence of any of these three things, we couldn't measure the reaction because it didn't occur. This will not just catalyze oxaloacetate by itself, it won't catalyze NADH by itself. They need to happen together right at the same time. So we did this reaction multiple times. When we heated it up, we found that the enzyme could denature in heat, pH, not much effect. But one thing we did find was that when we had oxaloacetate and NADH, usually we're going to be able to go this way because that's the way we're controlling. We could measure NADH. But when we had an overwhelming amount of product, NAD+, the reaction shifts. So instead, in the presence of high product here, the reaction will go this way. In the presence of higher product here, the reaction goes this way. And that's because there's so much malate and there's so much NAD that the enzyme pocket is flooded with these components, and it's catalyzing the reverse reaction. And some enzymes aren't reversible, but in this case it is, because it has two dual benefits. So what was the thing I wanted to see? Yes, so when we see equilibrium, so this is our absorbance over time, and remember we're measuring NADH. So we start with a lot, it's a huge heavy drop when we add all the components, and then it stops. The NADH doesn't fully go away though. What's happening right here, if you zoom in, is the amount of NADH is going up and up and down, but at a microscopic level that we can't really see. So at equilibrium, the reaction is actually going back and forth because there's so much malate and NADH over here versus the oxalacetate. You eventually get to a point with equilibrium where the reaction is going back and forth equally, and thus you see this like equal amount of gain and loss of NADH, but what we observe is a flat line. So hopefully that makes sense. That's kind of the key of what we saw for those two labs, was measuring that reaction and seeing. So that finishes the videos. Let me know if you need anything else. Definitely send me questions to clarify things, especially if I missed something. But otherwise, I think you all should be good.